Alright, next part is this for loop. Everything here being introduced is very, very important. So another for, if and for, these you use this a lot. Now we will use this example we've seen in class then how to generate this list. This n represent natural number starting from 1. So x is a multiple of 6 or a multiple of 9. This is union of a multiple of 6 and multiple of 9. So this is how I did it, just implementing this idea exactly into this Sage environment. First, we're going to go through, and whenever we found an element that satisfied the two conditions of the set A, we're going to collect them here in this square list. Name is wrong. It's not really square, but I'm just going to keep that name in here. It's about this example is about the for loop, and what we're going to do is that we're going to take this k in this range. This range here is a list starting from 0 ending at 99. And k is going to vary all the way from that. And we're going to do this following text and make sure you have indentation here, as you can see on all of them. First, we're going to store this value k divided by 6. This is not going to be a numerical value. It's going to be exact fraction expression in Sage. Temp2 is going to be k divided by 9. So we have these two quantity as k varies. So let's say k's beginning value 0 is going to be 0 and 0, and k is 1 is going to be 1/6 and 1/9. So this is the if command we just learned. Here we test that is k is divisible by 6 or divisible by 9. So this is floor command, is a common computer language command, is this integer part. What this does is that turn that temp1 into decimal numbers and take the integer part of that number. For example, if this was 1/6, that would be 0 point something. So integer part, that number preceding the decimal point is 0, so that's going to be 0. But temp1 is not 0. It is still 1/6 there, so it's different. That I claim this really determines whether it's divisible by that number or not. For example, if this is 12, when k is 12, is 12 divided by 6. The integer part is 12, and 12 divided by 6 is integer part is not 12, integer part is 2, and temporary 1 is 12 divided by 6, so that's going to be 2. So 2 is going to equal 2. And I have to combine with another condition which is connected by OR, so it is kind of exceeded this space out of it here. So you have to do a backslash and go to the next line. Make sure you have this indentation so that it knows. So this backslash and indentation is a continuation of that line. That's how it recognizes. So another condition is the second one here. Is this divisible by 9? That's exactly captured by this test in here. So if it's either divisible by 6, divisible by 9 flatly, if that any of this happen, we're going to store that number k into this list that we have prepared. If not, we move on to the next number. That's a for loop. So there is a bunch of tasks underneath this for. It's not just a list. You do things in there, and including storing your result in somewhere. So no indentation here. So after all that, it comes in here and lists this number. So as you can see, that's starting from 0, 6 and 9, 12 is a multiple of 6, not multiple of 9, 18 is a multiple of 6 and 9, and so on. They're all collected here. As you can scroll to the right, you can see all the numbers in there. Alright, in the second example, we're going to create this list of number that is a multiple of 6 and a multiple of 9. And in that, we're going to also introduce something called break inside the for command, for loop. And it's very, very useful. So here it's exactly the same thing. The k is going through 0 to 99. It's in this list, a range. And we compute this for quotient, temp1. And only difference is that here we're going to use and. Both this number is k is divisible by 6 and 9. Okay, and if so, we stored it in there. And I'm adding one more list here. It's just to introduce what this break does. So instead of going through all 99 elements, we decided to escape this loop whenever this condition is satisfied. So that's what this break does. Okay, so again, what this break does in this command is that we don't go through all this list, 100 numbers in there, 0 to 99, but whenever this condition is satisfied, we're going to break this for loop and just go to the next line. So up to here, we're storing this number into this list we're collecting. And then we're checking that number we have it here is divisible by 8 or not. So that's exactly the same type of condition we're putting up there. So if you look at this number 8 and 8 there, that's exactly determining whether the k is divisible by 8 or not. And this one we start with the k equals 0, so I had to exclude that trivial case, so I'd put it in there. Of course, we just want to test the case positive number. Whenever this happens, we're going to break it. So it doesn't show you all the multiples of 18 in the all the way up to 100. It breaks it whenever it encounters a multiple of 8 there. So it stops at 72. Right, next thing I want to do is just go through this exercise and use all those commands, and especially show you how to kind of organize your program whenever it's not just simple enough. You have to go through the several tasks, and I'm trying to show you how to do that. First of all, let me introduce this nice command, this built-in command in the Sage. It's called is something, so is square. It's asking if 34 is a square, and it says false. So if you use this command, picking up a square as we go through the list of numbers, that will be great, easy. But often that's not what we do in this course, so you have to kind of analyze and think about how to actually write this type of command, not use just simply using this Sage. So we're using this Sage as more of a programming language again than just using the extensive library of fancy commands they have. So is square and is prime, and those are available in there. But let's think about how to determine a given number as a square. First, let me explain this floor x. That was Sage command. That's an integer part of this real number x. So we, in mathematics, is usually denoted by this symbol, the bracket. So x, the bracket of x, is integer part n. That is captured by this inequality. This x is in between these two integers, n and n plus 1. If x is integer n, that makes perfect sense. You have the slide the fractional part introduced, and that's going to fall exactly into between these two intervals. So that's the notation in mathematics. So using that, let me write down equivalent statement. So if x is a perfect square, it's easy to verify that square root of m. Square root of x is m. M is an integer, so integer part of m is exactly m. This is something you have to think about the other way direction. If the square root of x and the floor of it, if that's... Sorry, the statement wasn't entirely correct, so I fixed it here. I've already explained that if x is a perfect square, you have this property, and I try to go backward. We have some integer given, and we calculate the floor value of m. And how are we going to know if this x is a perfect square? I think this captures it. If you get that integer part out of floor command, if you square that, you're supposed to get that x exactly back. So I claim that this two condition implies that x is exactly m squared. And you kind of get this idea by looking at, fiddle around a little bit. Again, when you prove it, you write down this clear statement and try to prove it as efficiently, as clearly as possible. So here we come again. Here we go again. Is square 34? We try to actually write a little program to do that, and I claim that we can do that using floor command. So here's a 34, and let me show you everything in there. It's pretty simple, and we're going to store that integer part of a square root of given value. So here's again integer part of the given value of the square root. That's m here. So here it is. That's stored as m, and I'm testing. And if m square is the given value, so here I square that integer part of the square root and square it and comparing with the given value. If this is so, we conclude that a is a square. If not, we print out a is not a square. So if you run this one, it says a is not a square. So I'm going to try that with the square, which is like a 36. And I ran it, and it said it's a square. 36 is a square there. So our original task is listing all the squares up to 100 using the condition. So what I did is that I separated the local task. We're given a number, and we'll be testing that whether a given number is a square or not. So I had this idea and wrote it down separately and ran some script in it. This is going to be something implemented inside the for loop. So this is what I mean by organizing your thoughts. Rather than trying to do everything in one cell, one command line, isolate the local task you anticipate that you're going to encounter, and separate it out. Run the commands like that, and has a run it several times and make sure everything runs correctly. So you have this separated task outside. Eventually, we're going to actually call this one a function, but right now I want to just introduce it this way and separate it, and separate those tasks and run it locally like this before we actually put everything into the for loop. But our task here is going to go through all these integers up to 100 and decide whether the given number is square or not. So here's how I did. So we're going to put those square numbers in here, and we start from k, starting from 0 to 99, and we stored those numbers in a temporarily, and this is the integer part of the square root of a, and this part is exactly what we have implemented here. So that's what I was talking about, that you implement exactly that little local task you tested before and put it in there. So if the square of this integer part of the square root is exactly the same as the given number, that means it's a square. Therefore, we're going to store in this list there. So go all the way up to 99 and list the squares. Then it gave this square as 1 and 4, 9, and those are exactly squares, right? Up to 99. It didn't include 100 because the range stops at 99.